About 25 years ago, I got a call from somebody in the National Research Council asking me if I wanted to chair a committee reviewing inertial confinement fusion. And my first question, of course, is what's that? And I had it explained to me, thought it sounded interesting, and that started a 25-year involvement with this field, which has a wonderful mix of technology, science, and applications. 20 some odd years later, the flagship facility that I was involved in endorsing is now running, and we're starting to get very interesting science out of it. And so I thought it would be of interest to this group to get one of the preeminent experimentalists working on that field to tell you all a little bit about the field, what the progress is, what some of the problems are, and what the potential is. So Omar Hurricane, whom I've known, I think for a decade at least.
At least 15 years, I think.
15 years. Is a distinguished member of the technical staff at Lawrence Livermore Laboratory. And his research focuses on high energy density physics, plasma physics, weapons physics. He's got more than 60 journal publications and an equal number of conference contributions, mostly in plasma physics, high energy density physics. Lots of awards, including the Lawrence Award from the Department of Energy. Many others. Bachelor's degree in physics and applied physics from the Metropolitan State University of Denver. Master's, PhD, and postdoc at UCLA. He's also been a visiting scholar at Stanford University in CSAC, the Center for International Security and Arms Control. He gives a wonderful talk. I most recently saw him in April, I think, and there's been quite a bit of progress since then, so he's going to tell us all about that.
Okay,
Omar.
super, thank you.
Good.
So I'm going to tell you about our progress. I'm going to first start off with a little background material to bring you up to speed on what's important for getting fusion. And in particular, the progress that's been made has been with this thing we call the high foot implosion campaign on the National Ignition Facility at NIF. And that's the NIF there. This is a picture of my laboratory, which is about a mile square. That's the National Ignition Facility, which is about the size of 3 football fields. And this other large building is the terascale computing facility building. Just for interest's sake, actually, the terascale facility actually uses more electricity than the NIF does. So let me tell you, here's what we do at that National Ignition Facility. So this is the control room. It's mission control for the NIF.
4, 3, 2, 1.
Energy is stored in a bank of capacitors that we discharge in a few moments into the laser system. The laser pulse starts in something called the master oscillator room, which sets the pulse shape for the laser beam. The pulse, yeah, we slow down at the time. Laser energy starts off in preamplifiers, sucking up energy from the capacitor banks, then goes into a set of full amplifiers, and the laser beam, which you see in the form of red light, bounces back and forth several times, picking up energy as it takes each pass. You see the cross-section of the laser beams is actually square. The light is red because that damages the optics the least, but as you'll see at the end, it will be converted to blue light, which is what we need for our experiments. The laser light then passes from the amplifiers into something called the switch yard, which breaks off the beams and sends them to the target chamber such that all the laser beams arrive at the chamber at equal time. The chamber is about 20 feet in radius. There's the conversion to blue light. There's our target at the end of a control stalk. The laser energy enters this metal can that we call a Hohlraum. That's German for hollow room. The laser light, which is in the form of blue light, hits the walls and is converted to a bath of X-rays. Those X-rays ablate, essentially explode the surface of the capsule, which holds our fusion fuel. That ablation process creates very large pressures which drive that capsule inwards, and if you're lucky, you get the conditions for burn. And it all happens in about 15 nanoseconds.
How big is the little capsule?
2 millimeters in diameter. So that's basically the way it works. As you can see, it's pretty straightforward. The whole trick that we're trying to achieve in inertial confinement fusion, ICF, is to turn about 100 million atmospheres of pressure, 100 megabars of ablation pressure, into about 300 billion atmospheres of stagnation pressure. And I'm going to walk through the target part of things. I don't actually know a whole lot about the laser itself. The laser, to me, is just a way to concentrate energy in a small volume. So here's this metal can that we call the Hall-ROM. It's basically an X-ray converter. It looks the same from the top and the bottom, but I'm only showing you the bottom here. This hole at the bottom is called a laser entrance hole. That's because that's where the lasers enter the Hall-ROM, which you see in here in blue and red. In the center of this Hall-ROM is this capsule. The Hall-ROM itself is about 12 millimeters in diameter. It is about a centimeter long. This capsule, this is an actual X-ray image of one of our capsules that we use, is about 2 millimeters in diameter. The thickness of this plastic shell, it's hollow. The ablator, which is the shell, for us is made out of plastic, and in this case it's 195 microns thick, although we do use other materials and other thicknesses. Coated on the inside of that capsule is a little fuel layer made out of deuterium, tritium. It's frozen and it conforms to the shape of the capsule. That's about 69 microns thick. That's a little less than the thickness of a human hair. And that's really the active part of the fusion experiment. So what happens is the laser energy enters this Hall-ROM. The laser energy that's delivered is in the range of 1.6 million joules, megajoules. Because of the X-ray conversion process being inefficient, you lose about 500 kilojoules of energy, so the X-ray conversion leaves you with about 1.1 megajoules. Those X-rays, basically you create a little oven of X-rays which bathes that capsule, causing the molecules on the outside of that capsule to break into atoms, the atoms to break into electrons and their positively charged nuclei, and those nuclei then heat up. And so where you had one material particle, you now have many, it's hot, and that causes the surface to explode at very high pressure, and that's where you get the 100 million atmospheres of pressure.
Excuse me, are you going to explain why you first go from optical to X-ray and not directly illuminate this thing with the optical?
I will describe that. I could answer that in questions. There are pros and cons to illuminating this capsule directly with the lasers, and that we'll get into a little later in the talk. The primary purpose of the Hall-ROM is to provide a smooth bath of X-rays, whereas if you try to hit that capsule with the lasers directly, imagine the surface of a golf ball where you pocket the surface. So that has the advantage of delivering more energy because this Hall-ROM process is inefficient, but you create the seeds for instability. And also there are other things that have to do with the hot electron production which can frustrate your ability to compress an implosion. So the compromise here is we trade off a smooth drive of X-rays for the fact that we're actually using up some of that energy to create that smooth drive. So that's essentially the answer to your question. And you'll see why we are worried about instabilities a little later. Because this capsule has a small surface area compared to the size of the Hall-ROM, it doesn't absorb all that X-ray energy. So you get a loss of about a decade of energy, and that's actually the advantage of doing what you were calling direct drive. It's where you put the laser energy directly on the capsule. You don't get this loss of energy, but again, you set up these seeds for instability and other problems. So we're using this indirect drive process. And again, it's indirect because we're not pointing the laser beam directly at the capsule. So this pressure...
Can you explain, how did you get the X-rays?
The laser energy here, which is UV light, hits the metal can, and you create inverse Bremsstrahlung, which creates the X-ray bath. So this pressure, which accelerates the outward side of the capsule inwards, gives you kinetic energy because pressure accelerates. And so this DT fuel ice layer, which is along for the ride, picks up some energy, but again, you lose about a decade of energy compared to what was absorbed by the capsule. But you gain a lot of speed. You go from a stationary state to about a speed of 370 kilometers per second. And the whole idea now is you're taking energy and you're converting it into energy density, because at each scale you're putting that less energy into a smaller and smaller volume. So what you lose in energy, you gain in pressure. And so in a way, you've taken this 100 million atmospheres of pressure and you're trying to achieve something on the order of 300 billion atmospheres of pressure. So the main purpose, again, of the whole process is to do pressure amplification. The implosion's purpose is to act as a pressure amplifier, and that's if everything works great. If things don't work great, it's actually a problem amplifier. The reason why getting high pressures is important is hidden in this relationship here. The energy that you need to get ignition actually scales as 1 over that pressure. So if you can get the pressures up very high, the energy required to start ignition off goes down. If you can't get the pressures up and you have a fixed amount of energy coming from your facility, you might not ever get ignition. So when this implosion is done and all that kinetic energy collapses in on itself, you create a stagnated state where kinetic energy has been converted into thermal energy, and you do PDV work. You now have an assembly of fuel and a hot spot in the middle if everything worked out great. So here's a little illustration of how that's supposed to work. That's the cartoon. Here's how it actually works. So this is a simulation of the target. There's the capsule in the middle. Here's the Hall-Rahm can. The lasers are entering from the top and the bottom in cones. Each set of beams from the top and the bottom, there are 96 beams, 192 in total if you include the top and the bottom. The gold can, you can see, is turning into a plasma as the laser energy hits it. That generates X-rays. As that occurs, those X-rays bathe the capsule in X-ray light, causing it to explode. And again, that explosion drives the fuel inwards. The laser pulse that's going into this Hall-Rahm is kind of carefully described with a precise power versus time in order to create particularly important conditions inside the fuel such that we can maximize the velocity and maximize the compression as best as we can. And we call this power versus time the pulse shape. So I'll use that term several times.
I wonder if it would be useful if you could just briefly describe the DT reaction and what ignition
Yeah,
is.
so let me get to that. So
Can I ask a question? How come the Hall-Rahm doesn't explode out?
because we make it thick enough that it doesn't. So it does move a little bit outwards. And if you give this enough time, we're only showing it here for 20 nanoseconds, it's exploding inwards because that's where the energy is going. There is pressure building up in this thing and it is kind of bulging outwards a bit, but on this time scale it doesn't completely blow up. It'll eventually completely blow up. And if we made it thin, if we made the wall thin enough, it would actually completely vaporize the moment the lasers hit it.
So do you have to replace the Hall-Rahm?
Yeah, this whole thing is gone. So every experiment, this thing, which we call the target, so this part, the Hall-Rahm, has the capsule in it. That whole assembly we call the target. The middle part is the capsule, and that DT ice on the inside is the fuel. That's kind of where the fusion is going on. So now, why do we go to all this trouble? Well, because we built this facility, but actually, so what we're trying to do is this. We're trying to achieve a particular condition for fusion, and it's called the Lawson criteria. It's basically a criteria of pressure in the fusing plasma and time. And we're trying to achieve a product of pressure and time that's sufficiently high. And it's of this order, 25 atmosphere seconds, although the number actually changes depending on the conditions. Magnetic fusion, which is one way of confining a plasma and trying to achieve fusion, what they're trying to do with a kind of 14-meter chamber that's a donut shaped, you confine the plasma with magnetic fields, is create pressures of levels of atmospheres, but you're confining the plasma for orders of seconds. And that's hard because plasmas tend to want to wiggle out of magnetic fields. For us, in inertial confinement, what we're doing is we have a much smaller target. It's not 14 meters, it's 1 centimeter. And again, this is 2 millimeters. What we're trying to achieve is very high pressures, 300 billion atmospheres. But because the target is small and the pressures are high, the time scales are small, so it only lasts for a fraction of a nanosecond. But the product of pressure and time is basically the same. And again, that's Lawson's criteria. Lawson's criteria basically comes from an argument about what the DT fusion, what is needed to achieve DT fusion. And so we'll talk about that here. So what we're trying to do is create fusion ignition. And that state is achieved when the net heating from fusion actually outstrips the cooling of your fusing region from electron conduction and X-rays. So here's our little ball of DT. Again, we have this cold DT fuel, which was along for the ride on this implosion, doing the PDV work as this thing implodes, and it develops a hot spot actually off the inside of that DT fuel as time goes on. And this is where the fusion reactions are meant to initiate. Again, we're trying to do DT fusion, so it's deuterium-tritium fusion. The product of DT fusion is an alpha particle, a helium nuclei, and a neutron. And if you get enough of these to happen, it's interesting. So the problem is, as you try to get that hot spot hot, Mother Nature likes to fight you on it. So what happens is that as you try to heat this up, Mother Nature tries to take away the heat in the form of electron conduction and in the form of radiation losses, Bremsstrahlung. So it's a battle between the rate at which you can do PDV work on that fusing plasma and these losses. The balance of that battle is represented here by this simple equation, which just represents this simple statement that the heating of your fusing plasma, this particular one is written in terms of gigajoules per gram per second, but you can write it in many different ways. The heating, so T is the temperature, little t is the time, increases as you do PDV work. So as you put PDV work in through this kinetic energy that you put into the implosion, you create heating. So d big T, d little t goes up. As you create heating, you get losses from X-rays, Bremsstrahlung, which carry away energy, and you get losses from electrons, which carry away energy. Rho is the density of the heated spot. HS means hot spot. R is the radius of that hot spot. And so you're fighting the rate at which you put in kinetic energy to create heat and these losses which carry energy away. If you're lucky and if you have the right conditions, self-heating starts to kick in. And once self-heating kicks in, things get really interesting because you see it's a positive term and it goes up as a rapid power of temperature. This particular writing is only good for between 3 to 6 keV, and I wrote it that way because most of our experiments are in that regime. So if you can beat out these losses with PDV work, you can get this temperature increase to feed itself into self-heating. The self-heating increases the temperature, which causes a bootstrapping effect that we call self-heating. If that occurs, you end up in this part of this space up here. So now if you take this equation, you can see there are essentially two important quantities. There's temperature and there's product of density times radius. So we often write this equation when dt is 0 and this term is 0 in just terms of temperature and rho r. That's what this plot is. If you're up here on this right-hand corner where the rho r is high enough and the temperature is high enough, you get this self-heating term, which causes the reaction to run away. If you are on this side of this plot where your rho r is small, but your temperature is high, this term dominates, and it means you lose heat very quickly from electron conduction. And if you're down here where the temperature is low but the rho r is high, the Bremsstrahlung carries away your energy. So what we're trying to do is we start out with something cold, and of course it's not dense because you can't make super dense DT. You start off down here and you're trying to get up here, and the battle is how do you find your way through this space. Got a question?
The self-heating is due to the nuclear reactions or not?
The fusion reaction creates an alpha particle and a neutron. If the rho r is high enough, or if the density here is high enough, you can actually cause those alpha particles to stay behind. And if those alpha particles can stay behind, they leave energy. Well, if they leave energy, they cause the region to heat up more. And if you cause the region to heat up more, you get more fusion reactions. And if you get more fusion reactions, you get more alpha particles, and so on and so on and so on. That's the way it works. So, and that's kind of captured in the next slide here. So there are two important quantities. Again, there's temperature, but actually this quantity, density times radius, is even more important. So we call this quantity rho r. I'll say rho r a lot because I'm used to saying it. But that means fuel area density. It's the mass density times the size. And it's key to obtaining an ignited state. And it's key because you're trying to stop this alpha particle that's liberated in the fusion reaction. So if you have low rho r, you make an alpha particle from fusion and it leaves without running into anything. so you've made some fusion, but it doesn't help, the fusion isn't feeding back on itself because this fusion product just takes off. If you have high rho R, you're packing things together very tightly, very densely, or you have a large volume, so you're kind of guaranteed to run into something eventually. In this situation, the alpha particle makes a contact with something and leaves energy behind. And you want that high chance of interaction, and that's all that rho R means. It basically tells you what your chance of interaction is. For our situation of DT fusion, what we're trying to achieve is rho R's of order of 0.3 grams per centimeter squared, and that's needed to stop alpha particles and ignite. There's another condition having to do with propagation, and that's when you get rho R's of order of 1 gram per cc. And what does that mean? Well, propagation means that, we started off fusion reactions in this hot spot, but we have all this fuel out here that we'd like to use. So ignition means we've gotten this hot spot to self-heat and take off. Propagation means that this hot spot now has enough energy to heat up a little bit of the cold fuel around it. That little bit of cold fuel around it then ignites. It becomes self-sustaining, and it ignites a little annulus of, or shell of cold fuel around it, and so on and so on. So you get propagation. So in a lot of ways, if you think of a stick of dynamite, most of the energy from a stick of dynamite comes from the dynamite, not the fuse. Okay? But you first have to light the fuse. This part, the hot spot, is the fuse. You get that to burn. You get that fuse to burn to the dynamite, and that's when you get a large liberation of energy. And so that's the way this process works. It's kind of two-step. You get the hot spot to ignite, and if the conditions are right, if the rho R is high enough, you get the cold fuel around it to also ignite through this propagation process. And that's eventually where we're trying to go. Okay, so the cartoon at the beginning, I was showing you that we basically take energy, we put it in a small volume, and we cause this implosion to accelerate inwards, and that concentrates the energy into a smaller and smaller volume. So that idea of pressure amplification, we also call compression. And so again, this is really what is key to making everything work. We're trying to compress the DT fuel in order to obtain that high rho R, that high areal density that I was just talking about on the previous slide. Now the physics of the conditions you need to achieve to get that rho R for DT are actually pretty simple, because DT, it's basically just isotypes of hydrogen, and that's a pretty simple material. So most of the equation of state is just governed by Fermi pressure. So the Fermi pressure for an electron gas basically goes as the density to the 5/3 power. A is the atomic mass, Z is the atomic number. Essentially, that is the equation of state for DT, although it's not perfect, because nothing is perfectly perfect as it is in the textbooks. So the actual DT pressure has a multiplier on it as compared to the Fermi pressure, and we call that multiplier the adiabat. And the adiabat is a measure of how much entropy we've put in that we'd rather not have, but just because these processes are imperfect, we get it anyway. So that multiplier is going to show up later and is part of the considerations of designing these things to work. But essentially, the pressure of DT goes as the density of the DT to the 5/3 power. Here I've written it in units. So alpha is of order 1 to 2 or 3, ideally. You want to keep that as close to 1 as possible. So the pressure in DT is basically 2.1 rho to the 5/3 megabars, where rho is in grams per cc. Okay, so the implosion that I illustrated to you in the movies and some of the previous slides, you can actually just write down freshman physics to understand how an implosion works if you know this equation of state. So the implosion means you're putting kinetic energy into the DT. You're getting it to accelerate to some velocity. The fuel has some mass m. Okay, but then it's a sphere, so you're collapsing it inwards on itself. Eventually, there's no place to go. So that kinetic energy is turned into PDV work. And that PDV work is what does the compression. So we take kinetic energy and equate it to PDV. So pressure times volume. Mass is basically density times volume. The volumes cancel, and you get a simple scaling. This tells you what's important. To get the density of the DT, the fusion fuel, up, you have to go fast. You have to get your high implosion velocity. And luckily, the scaling is really nice. For an increase in implosion velocity, you get a cubic increase in density. But what fights against you is this thing, this multiplier we call the adiabat, which is again a measure of entropy. If you put too much entropy in during your implosion process, you're never going to be able to get the densities you would like because this fights against getting the density high. And the stagnation pressure, which I told you earlier was key, because the higher you can get that stagnation pressure, the lower energy you need to get ignition, also scales in a similar way, where it goes up if you can get the implosion velocities up, but it goes down if you put too much entropy into your implosion. So what we want to do, ideally, is we want to get high velocities, but keep our implosion on a low adiabat. And there are other quantities that are of interest that you can pull out of this simple kind of freshman physics scaling. Basically, for facilities where you only have an order of kilojoules of energy being delivered to your fusion fuel, the scaling tells you what you need to design to. It tells you that you're only going to be operating with tens of microns of fuel, micrograms of fuel, sorry, at the hotspot level. You're going to have to get to very high densities, 1,000 grams per cc. That's huge, considering cryogenic DT in the laboratory starts off at 0.25 grams per cc. So you need a huge amount of compression to get the density up from something that a cryogenics engineer can make to what you need to get for fusion. The implosion speeds are high, as I was telling you. They were hundreds of kilometers per second. And the pressures that we are trying to achieve are hundreds of gigabars, hundreds of billions of atmospheres. And that's what it takes. And basically, it's all set by what the equation of state for DT is.
At Sandia, they used to have these long guns shooting.
Yeah, gas guns, yeah.
So this is more effective?
No, you can't get anywhere close to that. So just those gas guns, I only know the numbers roughly, but the highest performance gas guns that they have at Sandia, which are multiple stages, can get to velocities of about 10 kilometers to 20 kilometers per second. That's typical, and they use those for equation of state experiments and for materials experiments of all sorts. This is several, order of magnitude, a factor of 30 more than that. So it's a different regime. So, okay, so how do we do this now? I kind of told you we need to get the velocities up and we need to keep the entropy down. We need to keep that adiabat down. The way we do that is through designing, using simulation tools, a series of carefully prescribed shocks such that we can accelerate this layer of DT ice to high velocities but keep the entropy down. If you just smack this capsule with one big shock, which you might think is the right way to do it, you get that energy and just smack it, that heats it up too much. And that heat causes entropy. That entropy resists compression. So what we're trying to do is actually put in a series of little shocks, and that's illustrated here in something we call a shock plot. This is basically radius, although it says integrated mass. This is time. It's meant to be a radial profile of the shocks going through the different interfaces of the ablator, which is a part of our capsule here in the fuel. And these different red lines show the different layers in the ablator, because the ablator is actually a complicated structure of layers with our DT ice layer inside. So what we do is we, using simulation tools, arrange a series of shocks that come in one after another, appreciating the fact that every time you hit an interface with the shock, you create a transmitted shock and a reflected rarefaction or a reflected shock that interact with the next shock in. And we use a design tool, or simulation tools, to design this series of shocks to accelerate the fuel to high velocity, but keep the adiabat down. And the way we control it in the simulation is a designer will sit there, and a designer knows that the ablation pressure, basically the pressure that's driving the implosion inwards, is basically a simple relation between the radiation temperature, the X-ray temperature in that Hall room, and the pressure, and that drives the shocks and the acceleration. So every time you get a boost in temperature, you get a boost in pressure. Every time you get a boost in pressure, you can send a shock in. And that's what we call pulse shape design. And it also depends on the material. And again, this is the atomic mass, and that's the atomic number. So you choose your ablator materials, and you design a temperature versus time that gives you a pressure versus time such that you get the fuel to high velocity but keep the adiabat low.
What is B?
What is B? Oh, I've been meaning to remove that. It's this is an actual X-ray image of one of our capsules. Basically, we take an X-ray image before every experiment, and the engineer was pointing out that there's a flaw here, and it was flaw B. So there was a flaw A, flaw B, flaw C. I should remove that.
This DT, this frozen DT, is it hollow sphere or something?
Is it what?
Is it a spherical angular?
It's a shell. It's a shell that's about 70 microns thick, although we vary the thickness.
Inside there is nothing?
And inside there's nothing. There's gas of DT in partial pressure equilibrium with the ice, because there's a, you're near the triple point when you freeze these things, and so there is a little gas here. But
So B is nothing?
B is that little dot. See that little?
It's an imperfection in the capsule.
It's an imperfection in the capsule, so that we're seeing there. So you're doing a face-on radiograph. Let's see. Okay. All right. So.
I mean, you have this sort of gray. It looks like a graph, but it's sort of spread out and cloud-like.
Yeah. So.
What is that?
So this is a plot of log pressure. So basically, these are, when it's kind of just a little curve. You're following the shock wave in. That's a region of high pressure. This fan. Yeah, so now you kind of look, it comes to an interface between the ablator, which is plastic, and the ice, and then there's a reflected rarefaction, but hydrodynamics create a rarefaction fan is what it's called in hydrodynamics, and so you get a wave moving radially outwards. At the same moment, you get the shock wave moving inwards. So now this shock wave gets to this interface between the ice and the gas, and again, you get a transmitted shock into the gas, but then there's a reflected fan, a rarefaction fan that moves backwards. So what you're seeing out is a fanning out of this rarefaction wave as a result of the shock moving from one material into another.
There are 3 shocks coming.
Yeah, so you can see, there are 3 shocks. This is 1 shock, 2 shock, 3 shocks. This is time. So you see this first shock creates a transmitted shock, then a reflected rarefaction. So this next shock that we want to send in is actually challenged by that reflected rarefaction, and that's part of the design process, because if this rarefaction wasn't here, this second shock would be in a different location in time.
How do you send in? You send in
Pressure waves. Basically, we're hitting the outside of the capsule with pressure waves. The way we prescribe these pressure waves is by controlling the temperature. The way we control the temperature is through the pulse shape we ask the laser to deliver.
Okay, so in other words, the laser delivers a pulse that has a sort of a
It has that was let's go back. So this is this curve. So we're asking the laser for a series of pulses of power. First pulse, that's our first shock, because the temperature that corresponds to this drives the pressure. Second pulse increases the temperature, drives a second pulse of pressure, which drives another shock. Third pulse, fourth pulse, and again, it's up to the designer how many of these you put in and what it looks like.
Part of the problem is to figure out the optimum design of that.
Yeah, and it's, there's, when you talk optimum, it's a little dangerous, because there's always a trade-off. It depends on what you're trying to optimize on. So, but yes, essentially, it's up to the designer to kind of figure out what the time of those pulses should be. So, I kind of told you the principles, and here's kind of what's been achieved so far. This is a plot of fusion yield versus time. So the way we keep track of time on NIF is through shot number. The first 2 digits are year, second 2 digits are month, last 2 digits are day. And this isn't all the experiments that take place on NIF. This is all the DT fusion experiments, and for each one of these, you might have 3 to 9 other experiments that you use to prepare for these that are non-yield producing, because there are a number of things we have to keep track of. And so, I don't know how many of you follow NIF or the National Ignition Campaign, but there was trouble for a while where things were just not performing that well, and that's illustrated here by several years of yields that were, okay, but not really what were expected and not too high. So what's shown here on this plot, again, the bars are fusion yield. It's broken into 2 colors. The blue is the amount of yield that we expect from the compression, from the PDV work that we've done by prescribing this pressure and accelerating these things inwards. The pink is the yield from self-heating. And that's the part we were trying to get kicking in, where the reaction starts to feed back on itself. And ideally, we want the pink to be much larger than the blue, and that's hopefully where we're headed. The other thing that's shown on this plot is the energy delivered to the fuel, and that's shown in black dashes with some error bars on it. So you can see for a long time, the fusion experiments on NIF were not really producing high fusion yields. They weren't making up for the energy delivered to the fuel. We started our experiments back last May, not last May, but the year before. And we've kind of had a pretty rapid rate of increase over the last year, where we see a bunch of interesting things happening. We see finally, for the first time in the laboratory, we're getting more fusion energy out of these experiments than was put into the fuel. And again, the fuel is the last little part of the implosion. There's all this other energy that's wasted to get to that point. But we also see that we're actually getting self-heating yields, the pink here, that are actually larger than the yields from fuel compression. And that we call alpha heating, and that's a pretty interesting regime to be in. And again, that's the first time in the laboratory that that's been achieved. So what was the difference between what was going on here and what was going on here? So I want to just kind of describe that to you briefly. There are several motivations for changing strategies from what was going on before to what we've been trying recently. One of the big motivations was the fact that we thought instability was damaging the implosions that were going on previously under the National Ignition Campaign. That's what NIC stands for. And one of the ways we know that was occurring is by this inference we make from the data. And this inference we call mix. It's basically inferred from the X-ray emission coming from the hot spot and ratioing it with the yield. So what happens, because we know that Bremsstrahlung X-ray emission goes up as the atomic number squared, if we see the X-ray emission in an implosion become much brighter than what it should be for a given yield, we know that high Z material must have gotten into the DT region. And DT is low Z because it's basically an isotope of hydrogen. It shouldn't be emitting like that. So if it is emitting like this, we know that we got some higher Z material getting in there, mixing in there.
It got in there beforehand.
No, it got in there from the ablator tearing itself apart. So basically what's happening, it's not from the beginning, it's not from the gas they put into the implosion, it's from the implosion tearing itself apart on the way in, and I'll show you some illustrations of that in a moment. So we can infer under the National Ignition Campaign, as a function of velocity, you would hope to see this stay flat, but what happened is as they pushed the velocities up, there was a lot of mix, as inferred from the Bremsstrahlung emission kicking in, which implied that the implosion was not working the way it's supposed to. So what we did is our team changed the pulse shape. So this is that radiation temperature versus time. The radiation temperature, again, to the 3/5 power gives you the ablation pressure. So every time you see a bump up in this temperature, it means you've given it a boost of pressure, and that drives the implosion inwards. So in the low foot, the NIC implosion, the radiation temperature versus time was this black curve. And what we've done is we've actually changed that temperature versus time to look like this red curve. We've gone from a 4-shock system. Again, each jump in temperature launches a shock. So there's 1, 2, 3, 4. In the high foot, we have 1, 2, 3. And you can see there are other characteristic changes that we've made that make it look similar but different to what the low foot was doing. It's shorter in time. It's higher here during this little plateau that we call the foot, hence the name high foot versus low foot. In terms of the laser pulse versus time, it looks like this. Again, the black curve is the laser pulse versus time that I showed in that movie near the beginning. What we've done with the red is we asked for about twice as much power at the beginning. The trough here is higher, but you can't really see it. And of course, the pulse is shorter. And then we've also dropped this feature. And it's funny that you can just ask for a different laser power versus time and get such dramatically different behavior. The reason...
If you go back, the right hand curve is what you control to obtain the left
Yeah,
curve.
so exactly. So when we design these implosions, the designer is working with curves like this and changing the wiggles of radiation temperature versus time to get the pressure response versus time that they want. Of course, you can't ask the laser for a certain radiation temperature. What we ask the laser for is laser power versus time. So we ask the facility to deliver this in order to get this, and then get the implosion to behave the way we want.
You can measure the thing on the left.
We can measure the thing on the left, but it's a consequence of the thing on the right. And so actually the way we measure this is by looking at the tail of a Planckian, we measure energy in certain energy bins that are in the tail of a Planckian, and we can infer what the radiation temperature is by fitting that. And that instrument is called the Dante. Okay, so now why do we make this change, or how were we motivated to make this change? Again, the data suggested that the implosion was ripping itself apart. And that's illustrated here by these simulations of the low-foot Nick implosion. So what I'm showing you is what the implosion looks like at two different times based on what we believe from simulations. And this is a simulation assertion test. So this is an axis of symmetry. So take this thing and rotate it around the cylindrical axis. It's a capsule. This is a 2D simulation. This shows what the implosion looks like based on this simulation when the shell, which is the colored region here, is about 200 microns. Again, it starts off at about 1,000 microns radius. The color scale shows density. So as you can see, the simulation here is implying that the shell has a lot of what are called bubbles and spikes. It's really Taylor instability, starting to pull it apart. And then at peak compression here, when the implosion is about 50 microns radius, the ablator, which is the dark red region, has now kind of broken into pieces and flung bits of itself into what should be the hot spot. And remember, what this should look like, ideally, is a nice smooth shell, an annulus in 2D, surrounding a nice bubble or a nice spot, a round sphere in the middle. And it doesn't look that way at all. Now this is a bit of a simulation game here, because what we've done in this simulation, we've turned up the measured surface roughness of the capsule by about a factor of 4, and said if for some reason the surface roughness of the capsule was larger than what we thought, because these are man-made objects, they're not perfectly smooth, nothing in reality is, each little imperfection in the shell will grow and cause the shell to come apart. So what's happening here is every little depression in the shell, because there's high pressure outside driving this thing inwards, pushes a little bit harder on the points where the shell is weak, okay? And a little less hard where the shell is less weak. The parts that are weak accelerate inwards, okay? And leave the parts that are a little bit stronger behind. And that process amplifies in time, because every time you push one of these bubbles inwards, material flows to one side. And as material goes to one side, the mass goes down. As the mass goes down, it's easier to accelerate, and therefore it accelerates more, and so on and so on. So this is a nonlinear process that just gets worse and worse and worse as the implosion proceeds. And again, I told you at the beginning, ideally an implosion is a pressure amplifier when it works right. When an implosion doesn't work right, it's a problem amplifier, and one of the big problems is instability. So what we've done by changing the pulse shape is illustrated here. Again, this was an assertion that by changing the pulse shape in the way we illustrated, that we can smooth out a lot of those instabilities. So at the same radius of about 200 microns, which is when the shell is at peak velocity, you see it's a lot smoother than this case. And when it's at peak compression, although it's not perfectly round, it hasn't broken into pieces. And so you can still identify a center, although it has a funny shape to it, and you can identify a shell around this. But we've made a compromise here where we, and that's illustrated by the color scale, to get this resistance to instability, we traded off compression. And I spent a good part of the first part of the talk telling you how important compression was. We gave up some of the compression, not all of the compression. And again, there's that alpha quantity again. Again, we want the alpha to be as close to 1 as possible, and that's what the original optimization was based on. Try to keep the adiabat, the entropy, down, but that resulted in instability. Here, we've accepted the fact that we're going to put more entropy into this implosion, therefore we can't compress it as much. So green is kind of 12 grams per cc at this level, whereas the red is 24. So we're getting about half the compression, but we're getting less instability. And so that's kind of the game we're playing.
And you fiddled with the pulse shape to get this?
Yes, that's completely, we're using the exact same targets. Or again, we vaporize the target after each experiment, but they're ideally essentially the same target over and over again. And all we did is change the pulse shape.
And that's some kind of optimum, at least of your procedure.
It's a better optimum. Again, depending on what you're trying to optimize. We were trying to suppress instability to control this implosion because these just weren't working. We do it by changing the pulse shape. That's all there is to it.
Just a question about that. Why is that relevant not to turn and not changing the design of the whole around?
Oh, so that's an excellent question, and that was going to be the whole second part of my talk. But I'm going to have to go a little quicker here. What we are actually trying to do, and I'll get into that here. Let me skip some of this. First, I just want to show you how diabolical these instabilities are. So we've actually confirmed with other experiments that indeed by changing the pulse shape we can control instability, and a team of my colleagues has published this work. So we take one of our capsules, again in our case it's made out of plastic, you put controlled perturbations on the surface, we put a little periscope in it and we can look through this and we can take pictures at various times and we can watch the instability growth. And
This is inside the can. That thing on the left is inside.
It's all inside the hull rum. It's all inside the hull rum. And so what's happening here, look at this capsule here. This is density, this is temperature. This should look smooth to your eye at the beginning. But as the implosion proceeds, you can see these instabilities grow up. So everywhere there was a slightly thinner bit of the capsule, you get one of these bubbles going inwards. Everywhere you had a slightly thicker bit of the capsule, you get these spikes going outwards. That amplifies because implosions are amplifiers, and it rips itself to pieces at small radius. So this also shows what the radiation temperature is on the outside. You see it changing colors. It starts off cool, and then it gets hotter and hotter. That's a reflection of pulse shape versus time. So we can measure how much instability growth there is, and growth factor here is a proxy for instability growth as a function of mode number. The low foot Nick implosion had a lot of growth. With this change in pulse shape, we have much reduced growth, and that's what we've tried to achieve. Now, the question from the back of the room there about why not try other things. We are trying other things, and because we've only addressed one issue with this change in pulse shape, and the issue is control of instability. By controlling the instability, we can actually now use the experiments to probe other parts of parameter space. And so that bar chart after May of 2013 illustrates experimentally how we're trying different things to see what Mother Nature says are improvements upon the way of doing things and things that maybe aren't going to help us right now. So this is just an illustration of breaking down that bar chart into different bits where I show you what are the things we've tried. Well, we've tried this thing that we call coasting and no coasting. What that means is we turn the laser off early or we leave the laser on later. By leaving the laser on later, we put more energy into the implosion. So this class of implosions here, where we're high power, low energy, these implosions were high energy, lower power. And you can see an increase in fusion performance as a result of that. And then we have this set of experiments here where, again, for the same capsule, we just increase the energy that we're putting into the implosion. And you see a scaling of increase of energy and an increase in alpha heating. And actually, these were the first experiments, again, to kind of achieve fuel gain and alpha heating. And then we change different hull rums, which is one of the other things we could change. And we're doing it experimentally. We first do a set of experiments with the same laser drive in a gold hull rum. And then we try it with the DU hull rum, that's depleted uranium. Now we're using those parts of the periodic table because high Z materials are resistant to letting X-rays pass through it. So we like using those materials. And you can see just by changing the hull rum material, we got a 50% increase here in fusion performance and actually a doubling of fusion yield as compared to this one with the same pulse shape. And then we try thinner ablators. So here we go from 195 micron thickness ablators, that's about essentially two human hairs, and we're making it thinner and thinner. And as we do that, the fusion performance goes up. Now that one's particularly interesting because as we thin out the ablator, of course, we're driving less mass. So for the same amount of laser power and energy, we can accelerate that mass more because F equals ma. If the m goes down, the a goes up, the velocity goes up. But of course, as we make it thinner, it's more and more prone to instability. So there's a risk in doing this, but so far it's survived, and it's a nice progression of fusion performance just by making the ablator thinner. we try to repeat just to be just to be scientific, to make sure that we're not fooling ourselves every time we change something, and it more or less repeats. We tried this successful experiment with a depleted uranium Hall-ROM and then increasing the drive, and actually that was just a little better, not much better. And then we tried combining thinner ablators with these DU Hall-ROMs, and that's this scaling here, where we go from a gold Hall-ROM with 175 micron thickness ablator to DU. We tried this 165 micron ablator, gold, DU, and we see what the scalings are. And then we tried this thing where we changed the temperature of the DT fuel. We actually tried dropping the DT fuel down so that it compresses more, and actually didn't help us. Yeah, I know.
Each one of these just a single ablator? Each one of these?
Yeah, again, the whole thing is vaporized every time.
But each day, which you did an experiment, it corresponds to
One experiment, yeah. Yeah. So, these experiments, that bar chart basically marches through this parameter space. And one of the things we've seen coming out of this is that we have, now that we've controlled mix, we see that our implosions aren't as round as we'd like them to be, and that's illustrated here. These are side views of some of our implosions, these are top views, and these are neutron images of those early implosions. The red being the direct 14 MeV neutrons, and the blue being the downscattered. These were the first 4 experiments. As we go on in time up that bar chart, we put in more laser energy. We move up in the space of T-ion versus rho r. We got better control of the shape, but they're still not round. Again, this is side view. This is top view. So essentially, they're like compact toruses. As we tried some of these other variations of thinning up the ablators, we move up even higher into the space of temperature versus rho r towards ignition. Again, we see what these implosions look like. They're still not perfectly round, but by thinning up the ablator, it looks more round than before. Here's the set of experiments using the DU Hall-ROMs, which give us really quite nice performance, but we're asking a lot from the laser. That's about as much as it can deliver. And we see from going to a gold Hall-ROM, this is side view, to a depleted uranium Hall-ROM, we've controlled the shape. This is the top view. We go from a donut to something that's more like a sandwich, but that's a 50% increase in yield. And then finally, we get up here where we have our best fusion performance to date, which is the closest to the ignition boundary, by combining a DU Hall-ROM with one of our thinner ablators. Although the shape of it is still not perfectly round, although it's pretty good. You know, there's a side view and there's the top view. And so,
scaled in microns.
oh yeah, I'm sorry. So this scale here, the diameter, that scale is in microns, so that's 50 microns, that's 100 microns. So this is roughly about 70 microns in diameter. Again, that's smaller than the width of a human hair, which is quite remarkable. But the pressure in that little spot is, you know, several hundred gigabars, several hundred billion atmospheres. The radiation temperature is on the order of 4 or 5.5 kilovolts, and the rho R's are about a factor of 0.15. So all of this is allowing us to see, by controlling instabilities, we see now that we have other issues that we need to address, and that's presently what we're trying to do with our program going forward. We want to bridge from this point here to ignition, but we need about a factor of 2 more in rho r to get there, although the temperature is pretty good. And so what we're doing this next year is we're trying to improve that shape. Not only the shape at the end, but how it gets to the end. Because the implosion, we have data that's telling us this implosion is going through oscillations on the way in. We want to stop those oscillations because it means wasted energy. We want to increase the velocity because there's a very strong scaling with velocity, and we want to capitalize on that. But we also need to start giving back some of that entropy that we took to make these things more stable. So what we're talking about is evolving our design, because as was mentioned, you know, the thing we addressed was not necessarily the only thing that needs to be addressed. We have to look at other parts of the parameter space. And so, again, so what our strategy is for the future here is better shape control, higher velocities, lower fuel adiabat, And we're also using this implosion that's now dealt with mix to be a tool for learning and figuring out what Mother Nature lets us do and what she doesn't let us do. But we've gotten some good results so far where we have alpha heating, we've gotten fuel gain, and we've controlled instability. And so with that, I'll end. So, yeah. Sure.
Probably stupid, but why cannot you, since you have so much trouble exploding this little bomb, cannot you dig a big hole in some basalt or something?
Yeah.
Explode a big bomb and harvest the resulting energy?
You know, we've done that, but people get upset, so. So actually.
No, I'm semi-serious.
You are serious? Okay. Yeah.
Why cannot you harvest the energy of a bomb if you explode it somewhere deep underground?
Yeah.
It's hard to get to this energy or something?
No.
Because obviously you are way off from using this for useful purposes.
I want to.
Useful energy.
Yeah.
Useful energy.
Yeah. So that gets back to this scaling here. So if you have a lot of energy, and I'm not at liberty to say where you might get that energy from, then the conditions that you have to get to in stagnation pressure are much, much relaxed. So if you have large amounts of energy available, because you're not using a laser but you're using something else, you actually make it much easier on yourself. So in a way, you are right. This is the hardest implosion you could possibly do, because the amount of energy we have available requires us to get to these enormous stagnation pressures.
But is it a problem you cannot solve, harvesting the energy of a thermonuclear bomb?
You've heard of the Cold War, right?
After all, they wanted to make a rocket with bombs.
Yeah, that was Project Orion. That was Project Orion. That's a neat story.
Was it like thought about and have you decided that this is not going to work or something?
No, let's see, what can I say about this? The one thing I can say is there was a program called Halite Centurion, which you can look up on the internet. And I think that will answer your question. And
say again the name, sorry.
Halite, Halite -Centurion, like a Roman centurion. Look that up on the internet. And
I think the official statement is that that program established the proof of principle.
Okay. I wasn't quite sure the words I'm allowed to say.
Don't they do that in Russia exactly? And in that place, I mean, besides that sort of thing? In Sarov, I think you should check that.
It's an international community doing this.
Yeah.
The French are building
the French are actually collaborations on this, and so are the Brits. So, yeah, go ahead.
More prosaic question. Just if you make a change, like you change this profile for the laser energy, how long does it take to do one of these experiments?
Okay, so there are many ways to answer that. So we can actually, the facility has demonstrated the ability to do, several experiments a day. In practice, though, for these experiments, there's more time involved in setting up with that. So one of the things that's involved in that time is deciding, based on the last set of experiments, our analysis of it, what to do next. So there's a certain analysis time. So if you include that, it could be several weeks. In fact, once we've decided what the pulse shape is going to be, the experiment can be pretty much set up in a week. Most of the time in setting up these experiments is trying to make that cryogenic ice layer of DT, because we don't want a very messy ice layer. And it's a bit of an art and a science, and there's a team of really great people who make that ice layer, coating the inside of the capsule. But it's a trial and error process, and it's a lot like a snowflake. Each one is a little different. So they'll make one. Is it within what we will accept? Yes, great. If not, melt it, try again. And that process could take up to a week to do.
What are the tolerances on the
with the tolerances that we want. Oh, there is a roughness tolerance. There are also basically a tolerance on grooves, which are essentially cracks in the ice. And then there are tolerances on the low mode shape. We have a whole set of specs that they...
10 nanometers or something?
No, it's not that strict, actually. Yeah, it's usually fractions of a micron. Yeah, so.
But by reducing some of your powers and putting there something else, probably you can use it for materials line.
Yes, and actually we do that. So
Nobody else can do this.
the
Very unusual condition.
well, again, these conditions are unique now in terms of fusion and in terms of other science, so we can explore, you know, the conditions around alpha heating, an alpha heating dominated plasma. There are other things that the facility can do that aren't involving implosions, where they do material science experiments. Again, using the fact that you can concentrate energy to small volumes and use pressures. There are basic physics experiments. There are a lot of things having to do with emulating astrophysical environments or studying instabilities, which are ubiquitous for us and for astrophysics, and a whole bunch of other applications. Yeah.
Suppose you run the magic combination of all-around design, propulsion,
Yeah.
and all that. All of a sudden you have a working source of power, and so you build a plant that's roughly along these lines. How bad is are there radioactive byproducts that are a serious problem?
Well, you know what? These fusion reactions make neutrons, and neutron activates materials, and that's the one of the issues that people doing fusion have to deal with. Those neutrons tend to degrade metals by dislocating atoms, and so metals can become embrittled. The concept is, if it works perfectly for energy production, is you absorb those neutrons in a lithium blanket, and that basically carries away the heat, and then you pump liquid lithium to some heat exchanger somewhere to drive a steam cycle, ideally. So, and you breed tritium, and breed tritium. Yeah.
You know, there have been lots of studies about what it would take to make energy.
Yeah.
That's a ways off.
It's a ways off, and so I basically look at this as we're trying to figure out what does it take to actually make it work at this scale, and leave it at that. Once we see what it takes, if we get there, then decide how to make it practical. But if we try to overload ourselves with trying to make it practical before we even make it work, you know, to me that doesn't make sense. But
so how does the world change? How does the world change if you manage to do it?
yeah, that's
what opens up even at one shot every?
well, you know, I think for us, we're already at the regime where we're making this level of neutrons. There are nuclear cross-section measurements that could not be done before that we can now do. And so we have a lot of nuclear physicists who are involved in trying to use this implosion that we have to do measurements of nuclear cross-sections and reactions in flight. As we increase the fusion performance, that field opens up. The other interest is basically, this is kind of the history of technology. Once you demonstrate that something works, often there are many ideas that just pour in on how to make it more sensible, how to make it work better. Lasers are an example of that, and so forth. So there are things we can't foresee that hopefully it will open up for us. Yeah.
Good. Thank you.
Yeah, sure. Thank you.